And let's move on to our next talk. We have Daniel who's going to speak to us about a customized distance metric for explainable in situ solar wind clustering. It's another online talk, so we'll try and get it set up now. Okay, we see your slides, Daniel.
Yeah. Hello, everyone. Can you guys hear me?
Yep.
Okay. All right. Let's see. Oh, hold on.
Yeah, that's great. We see a full screen. So I'll give
Yeah.
you.
Just there. You go. Okay. All right.
Go ahead. Right. I'll give you a shout in 15.
Okay, perfect. Thank you. All right. Good afternoon, everyone. My name is Daniel Carpenter. I'm a graduate student at University of Michigan. Today, I'm here to go over the process involved in trying to customize a distance metric for explainable in situ solar wind deep clustering. I would like to thank my collaborators for their guidance while learning the disciplines involved in this work, and for the MCH organizers for hosting this event and having me talk. To begin, I'd like to actually start with an example to define with some of our terms. So distance metrics are how we discern between different samples. And so here I have a very small data set of 3 dimensions, the latitude, longitude, and elevation. And we can measure a distance between these 2 samples to quantify their differences. And we can also observe some qualities that can be inferred by these characteristics, such as total hours of sunlight being quite similar, and how local time is literally a night and day difference. And so the question is, how does this matter for our in situ solar wind? Well, physical measurements of the in situ solar wind can be characteristic of their coronal source regions. Solar wind is commonly separated between faster or slower proton speeds. And we traditionally, we oppose this sort of bimodality, but interactions with transient events such as stream interaction regions causes the resulting wind conditions to be mixed and changed by the time it reaches the spacecraft. We have quantities such as the heavy ion composition and charge state distributions, which remain frozen in past the release points in the solar corona. So these measurements are important because they can be used to constrain formation models, and they serve as signatures for the in situ solar wind. And as an example of kind of the type of data we're talking about, we have the ACE spacecraft here on the right, which lies in the ecliptic, and it receives a lot of mixing from different source regions. Trying to sort of unpack and infer these coronal conditions from the in situ observations is pretty crucial. By learning more about these groups of solar wind, we can learn more about how they were released and formed. So the question now is, should machine learning be used to approach this problem of solar wind characterization? And the technical answer is no. We've been able to statistically infer coronal features from in situ data in the past. But there arises this issue when determining the boundary between solar wind groups that while, qualitatively there can be a lot of agreement on, but when you get down to the, quantitative boundary of them, it's a little ambiguous. And so we then look to machine learning to sort of determine these decision boundaries for us and form a data-driven approach. Machine learning has successfully visualized and clustered solar wind data of several different observation types, which I will refer to as dimensions here in the past. But something that could be explored more is how some of the input configurations of these methods, how do they translate from the data to the downstream clustering that we see? And by making this process more explainable, the machine learning approach becomes less of a black box. And one of these aspects is that we're going to particularly explore is the distance metric, the choice of discerning between different types of samples in the solar wind. So here, we're going to set up a roadmap for explainable in situ solar wind deep clustering. You need to be able to connect parameters and configurations throughout the machine learning methodology back to the domain of our data, answering what are some of the physical implications of what we had set for our method. We can then learn what some of the optimal configurations to show the largest differences in the solar wind types. And all of this is to ultimately prepare for a customized approach to characterize the in situ solar wind, which should leverage the most effective parts of our previous exploration, yet be easier to understand in how it arrives at its output, because we have a better idea of how all of these intermediate parameters and configurations contribute to the larger picture. And for the time constraints, today we'll be just mainly focusing on this first point, namely with different distance metrics. So this approach will involve dimensional reduction stacking. For our data to start, we'll use a tiny subset here as an example. This is data from the Advanced Composition Explorer, which I showed earlier, where the data is averaged in a time series for every 2 hours. And we're taking just a subset from solar maximum as a starting point. Our composition and charge states are frozen in by the time they're released from the solar corona. So they are quite useful in determining what our clusters are like, and then eventually relating them back to coronal features. We'll also include proton entropy as well, since it only changes as much as 10% past the corona. So it's still quite useful to explore in this regard. We're going to remove coronal mass ejections. Now, this is an interesting point because CMEs might bias our result. So we'll remove them here to analyze the ambient wind, but it's important to note that with careful treatment, we can focus on these coronal mass ejections and then potentially identify them based on these wind characteristics. This sort of process is generally kind of agnostic to the specific types of things that you're looking at. We're going to normalize our data so that the magnitude of any one quantity does not bias the results. And then ultimately, we're going to use a combination of reduction methods to produce a low-dimensional output that we can then cluster and begin to take apart. So the first step after getting our normalized data along each dimension is to reduce the dimensionality. Now, principal component analysis is a linear transformation method. There is no machine learning happening here yet. By forming an orthogonal basis aligned to the variances of the data, we use principal components to preserve global structure. And we have some leeway here in how the dimensionality that we reduce to, because when deciding the number of dimensions, we can choose a number of PCs algorithmically, either by choosing a cumulative explained variance of something like 95%, or we can do what we did here by shuffling the data along the principal components and comparing it to the average explained variance. What's crucial here is that it is still possible to back out to our original data from this point. We just simply need to invert the steps that we used. So why is this important? Why apply PCA first? Well, what we're going to do is use this preservation of global structure to then calculate our distances. And this is where our concern of how distance is measured comes in. We use a variety of metrics, mostly those that are applicable to this data type. So we exclude things that are like Boolean values to calculate distances or the differences between samples from our PCA production. And by varying this metric, we can examine more closely how it impacts the downstream clustering. And crucially, this is from the PCAs that the principal components that we keep that well capture the global structure of our original data. And why this is important is because then we're going to apply it to our second dimensionality reduction method. And so we used t-distributed stochastic neighboring with embedding. And with these distances pre-computed, we feed them into our machine learning algorithm. PCA uses the distributions in the data to learn its topology, and it relies heavily on a configuration parameter we choose called the perplexity. Now, this is a weakness of t-SNE, and I can talk a little bit more about this later, but the perplexity value is not exactly explainable. And part of this work is to focus on how the perplexity affects the physical quantities of the clusters that we can find from what's called the embedding, or the two-dimensional representation of the data. These points now in this two-dimensional representation align with the original data samples, but it's now in a form that cannot be easily backtracked like how we could before. So we would need to do some what's called probing learning to see how these tuning of our machine learning algorithm affects what the physical values that we see are in our clusters ultimately. It does really well at showing the local smaller scale behavior, but struggles with the global behavior, which is precisely why we applied PCA before. So what do these look like when they're clustered? So we applied a clustering algorithm called DPScan, and now we can actually begin to look at what some of the physical projections of these clusters are like. DPScan has two parameters that we set, which are the minimum samples, which determines the smallest number of points that need to be neighboring a point in order for that to be considered a core point, and then epsilon, which is the distance from a point in which it could be considered a neighbor. DPScan is configured right now to be relatively strict with our embeddings, but these are values that can be adjusted and changed and require a little bit of domain knowledge in order to properly establish. The top row, so we're choosing two distance metrics that we calculated before and looking at how they are clustered afterwards. The top row here is the Euclidean metric, and the bottom row is Mahalanobis. And they're both presets from our distance function library. And you can see that there are quite a few outliers in several parts of these from the configuration of the clustering algorithm that we've used. But when we project the labels onto the physical parameters that we've originally used, we can see some interesting results. So the first ones that I would like to point out to are the 07 plus to 06 plus charge state ratio. And you can see here on the higher values of the 07 to 6 ratio, there are the purple and the pink clusters here that are corresponding to the embedding that seem to have higher 07 to 6 ratio values and sort of tail off to the lower ones in their normalized histogram. And then conversely, you have these blue and yellow clusters that are on the lower side, and they tail off to the higher. And that ordering, when you look at the proton entropy, the log 10 of the proton entropy, is kind of the opposite. The blue and the yellow clusters are higher in the proton entropy and lower in the pink and purple clusters. And this aligns fairly nicely with what we understand for the slower speed wind in the pink and purple clusters and in the faster speed wind with the blue and the yellow clusters. As a matter of fact, their overlap is actually at a quantity that's kind of special in that it was previously determined in literature to be their determination point between solar wind types. So this method that didn't have any prior like model input or physical guidance, rather, is able to sort of find some solar wind types that kind of align with previous understanding for these coronal features. And here for our other distance metric, you see that there's kind of a similar story. For here, the slower wind is in two groups, and the faster wind is only in a single group with this sort of broad, mixed signature type kind of interspersed in the middle of it. But again, their sort of overlap is at least quite well understood. So you can imagine that we can combine these distance metrics in order to form a customized distance metric. But what we've found is that the process is a lot more complicated than we initially thought. So the customization process requires something that I mentioned before called probing learning. And what I wanted to highlight here is that we've begun to test fusions of these distances while evaluating the results. But we haven't gotten anything conclusive yet, and this is because there's many ways that this process can be altered, and we get better understanding and explanations when we actually probe the effects of these results. we could stop at optimizing for a single iteration of this process, but the work is a stepping stone to actually making our own algorithm that's best suited for these in situ solar wind data. There's things like other spacecraft that we need to try out. We want to make sure that we can count for solar activity, potentially other even scaling methods that are all various things that what we need to do is we need to see how, when we actually compute our downstream clustering, how these clusters actually behave, what their physical quantities are like. Some distance metrics, some configurations might be really good at highlighting different types of solar wind than others. So when we combine them together, we can attain a means of discerning between different types of solar wind in an explainable and effective way. So in summary, we took a deeper look at how distance metrics discern between different groups of the in situ solar wind. We continue to find that machine learning remains a useful and evolving tool for visualizing and determining these boundaries between latent groups within the solar wind. And obstacles such as explainability can at least be approached through a methodic and careful analysis of the parameters, which contribute to the final result. With that, I'd like to thank you for your time and answer any questions if you have. Thank you very much.
Great. Thanks, Daniel. That was a very interesting talk. Let's just go to any questions that we have here in the physical audience. I see one down the middle, another one there. So,
hey, thanks for that. That was really interesting. Do you mind explaining to me, because I don't really understand a lot. You said that it's difficult to go from the TSNE PCA, well, the PCA was easier, but the TSNE back to your original data, and then you show the, I think, oxygen, the next slide. This one here, sorry. So my understanding is that it's hard to go from the TSNE on the very left to what you show in the middle and right, but here you are doing it anyway. How do you do that?
Yeah, so what I mean by that is that the TSNE, applying that machine learning algorithm is not necessarily a reversible process. We could not supply an embedding and get back our, like, let's say if we take 3 PCs, we could not get back that 3-dimensional data that we originally had. But the points themselves still align to the initial data set, to the samples of the initial data set. Their positions are basically represented in a low-dimensional, kind of like a manifold, not exactly a manifold learning, but so let's say like the first point in the embedding, that corresponds to the first point in our data set that we used. So what we can do is when we cluster on the embedding, we take our labels that are of the same size, same order of our input samples, and then we group the physical quantities of our original data by the labels that we clustered it on, so we can project it onto those values. And in that way, we can better understand what those physical quantities are, because it is like, so it's not like, so the point is that it's not invertible, but we can still relate it back to our initial data, which is kind of crucial. Otherwise, we wouldn't be able to use this to analyze these wind types.
Okay, brilliant. Yeah, that's answered it perfectly for me. Thank you.
Great. I think we have another question. Manolis?
So, Daniel, thank you for this interesting presentation. It was interesting to see that you tried pure statistical methods like PCA alongside machine learning methods to try to see how you can make better sense. Although I could not understand all the details. Let me ask you this. Do you think that machine learning in this particular problem is a necessary approach? Is it necessary to go about doing machine learning, or you can apply whatever advanced or sophisticated but statistical, conventional statistical methods you can apply? That's one thing. And then the second, if you have to apply machine learning, where do you see the interpretability coming out from? what are the steps that we need to be taking in order to understand or be able to interpret the results that we get? Thanks.
Yeah, these are both points that are very important to me. For the first point, why should this problem be approached with machine learning? Is a very good question. People have in the past used statistical methods to form these solar wind groups from the in situ data, and it's rather successful. Some of the methods have even involved like connection science and ballistic mapping to identify the actual locations where the in situ observations were, at least where we can approximate where they came from, so that we can relate them back directly to their source features. However, there's an issue that tends to arise where, for one, like at any one point, we can really only visualize 2 or maybe 3 dimensions and show the separation of groups in that dimensional space. And 2, the boundaries that we define, while they could be statistically significant, they might not be necessarily unique. And so there's a desire to have a data-driven process be used to determine these boundaries in a way that we would simply tune the algorithm and have an interpretable process, but leave the decision boundaries to the algorithmic approach. That way it's a lot more repeatable. If someone by eye was to look at different clusters of solar wind in let's say a 2-dimensional space, they might make a couple of boundaries that might differ slightly from others depending on what methods they use. So it kind of helps unify some things in an approach. For the explainability, part of this is to directly try to improve the explainability of these methods, because there's some machine learning algorithms that are completely explainable. Like there's been studies clustering solar wind using k-means, for example, but there's some advantages to more complex methods like dimensional reduction in order to extract these clear features in the solar wind data that in some cases help them perform even better as well in actually finding unique solar wind groups. So on that end, there's this work is basically trying to address the interpretability and the explainability, and this is by no means a trivial process. There's we need to make sure that we see the full scale of robustness for how these clusters are made. And then we need to do work afterwards, not only projecting these values onto the physical parameters, which can help us understand what the qualities of these clusters are like, but also do more work to relate these to their origin conditions. So, for example, like with Ulysses, there could be work done to associate the observations with their latitudes, for example. And if you see, you're getting your faster speed wind, you're getting your low charge state ratio wind at these higher latitudes, you can more assuredly say that these are aligned with polar coronal hole wind, for example. So it's one that needs a lot of caution, but through a methodological approach and through a lot of different ways of relating it back to the original data, I think we can provide some sufficient interpretability for these results.
Great. Thanks, Daniel. Is there any other questions from the room? Oh, we one more.
Thanks, it was a great talk. My question was about, you discussed the kind of the Euclidean matrix, which is pretty much typical for the physicists. But as far as I know, as you go to the high-dimensional data, some high-dimensional inputs, sometimes it breaks down. So the point is that the problem if you have high-dimensional data, the variation in distance between 2 different points, it's I mean, that doesn't change. There is no variation. People at some point go to another type of more simple but more strange type of metrics like Manhattan metrics. Therefore, I would like to ask you which kind of dimensionality. I mean, it works for you very well, but what do you think to consider probable? Or have you seen some problem when you went to the high dimensional input? Thank you.
Yeah, very good question. Yeah, we actually ultimately do not want to rely on Euclidean metric, precisely for the reasons that you've mentioned. In this case, it seemed to work fairly well, but for other ways that we've, tuned our machine learning algorithm, Euclidean did not show as clear distinctions in the different solar wind types. And so one of the things is definitely to try to move away from Euclidean because it's fairly commonly used, I would say, in not just like solar wind clustering, but a lot of different clustering problems as well. But it's problematic in some ways. Yeah, we did look at things like Manhattan distance as well, and there's a few others, like some that have been like used in solar wind clustering analysis. But have not really been like thoroughly explored as to why, are things like even correlation distance metric. So what we're going to do is we're going to try to apply a fairly wide array of potential distance metrics, and even some that are modifications, like including Chebyshev and then a low rank approximation with Chebyshev, to see how they differ. And see how it affects the downstream clustering. We need to explore this array so that we can make better inferences as to what these metrics are causing for our solar wind data, because it's not with just looking at our data set, it's not immediately obvious. If it's like a Manhattan, or if it's a different distance metric, or if it's a combination of several in a sort of fused distance metric, that would be ideal in this case. So that's ultimately why we want to make a customized metric.
Great. I think that's all from the physical audience. We have a question online, if you want to go ahead.
Hello. So I'm really excited to hear you talk about distance metrics. I think they're really important. I have what might be quite a technical question that you maybe can't answer right now, but I was really interested in the second dimension reduction technique, and I was wondering if you're able to tell me any more about how it is capturing the topology of the embedded data.
Oh, sorry. Yeah. So. So I'm trying to think of the best way to phrase this. It utilizes T distributions of that are applied to its input space. So like first, like it starts out with like a random initialization. You can set it to be predefined, which we might do in the future. But it then uses these T distributions of the input data to determine closeness or their neighboring. And it iterates and it loops through a stochastic gradient descent to basically reach a stable embedding. You can actually change things like number of iterations and learning rate with this type of method. Yeah, other than that, what I can do, if you want afterwards, I can reach out and provide you with some more resources on a lot of more technical details, because it could definitely be its own talk.
Yeah, I would love that. I was going to follow up anyway, because I think I've got some citation, I know of some papers that I think are very relevant in various aspects. So yeah, I'd love that. Thanks.
Yeah. Thanks. Appreciate that.
Great, thanks. I actually just have a quick follow-on question, particularly about this aspect. Have you tried any of the other methods like UMAP instead of a TSNE?
I'm so glad you asked that. Yes. So there was three main things that we wanted to look at for sure. So we wanted to look at t-SNE as a sort of baseline. I wanted to use PCA plus t-SNE stacking to try to improve the results because t-SNE kind of struggles with some global behavior. And then, yes, we wanted to look at UMAP plus PCA because that has also been found to have some really effective results at being able to form a representation of the SolarWind data. What's nice about that is that UMAP has it's a lot easier to control the sort of parameters that you're using, a lot easier to account for them. It's very good at capturing a balance between global and local behavior. Yeah, that is definitely some of the, when I talk about like some of the reduction methods, yeah, I should have included that there's a few different approaches even that we want to try out. For UMAP, we would do the distance pre-computation in the beginning, and then our current situation is to reduce to let's say like a set number of components. Like if we had like a really high input data space, we maybe do like 10 components, and then apply PCA to just take the 2 PCs, and we would cluster from there. But yeah, it's a very good question. UMAP is absolutely one to consider.
Okay, great. Let's thank Daniel again for a really interesting talk.
Thank you very much.